Hi, everyone. Thanks a lot for being here. I mean, it's 4:30 on a Friday, so I'm really, to be honest, kind of a little overwhelmed by the crowd. I'm going to talk about why software engineering best practices fail in data engineering. And if you want to follow along on your phone, the slides are at the QR code in the corner. Anyways, let's get into it. So first, who am I? My name's Constance, and I used to cosplay as a data engineer, which is to say I've been the person frantically debugging a pipeline at like 2 a.m., and I have a lot of opinions about why pipelines break. So these days, I'm a staff product manager at Astronomer, which means I get to look at the data behind those 2 a.m. pages at scale that's, to be honest, a little bit absurd. So who's Astronomer? Astronomer builds Astro, which is a managed Apache Airflow platform. And Apache, for those of you guys who don't know, is the open source Python orchestrator for data pipelines. If you've worked in data engineering, you've probably run into it. And if you haven't, you can think of Airflow as like really fancy cron with built-in reliability and observability. And so the data in the talk comes from real customer workloads running on Astro. Before I get into this, I'm actually just really curious though, like who in the room is a data engineer? Okay, so honestly, this talk might be fascinating, but it's actually not really for you. Who is a software engineer? Okay, yeah, there we go. So whether you're a data engineer or you work alongside one, you've probably seen this happen. Like a pipeline fails, the dashboard goes red, and someone in Slack asks like the question that always gets asked, like what changed? You start running through the usual suspect list. Maybe it's like a schema that drifted upstream. Maybe it's a file that arrived late. Maybe somebody updated a library version. But the one the most teams reach for first is the last deploy. The data engineers in the room know it's almost never the last deploy, but the instinct still tugs, especially when a stakeholder is waiting for an answer as to what happened. The deploy is the most legible thing on the suspect list, so it's where people tend to look first. So in application development, that like instinct isn't irrational. In app dev, it's usually right because code controls behavior. You write the code, the tests pass, the deploy goes out. The behavior in production matches the behavior that you wrote, and life is great, sort of. The whole modern software engineering toolkit, so like CI/CD, dev environments, code reviews, unit tests, feature flags, even rollbacks, are built around one shared assumption, which is if you control what ships, you control what breaks. And in application development, that assumption really does hold up. It's the foundation we've been building on for the last 30 years, and it works. So data engineering inherited this entire playbook wholesale. So CI/CD for DAGs, pull request reviews on every change, unit tests on transformation logic, rollbacks when something looks wrong. So we took the tools that worked in app dev and we ported them straight over, and the whole operational model that comes with them. So the deploy is the moment we treat as load-bearing, and it's where we put in the safety checks. It's where the gates have traditionally lived. And again, it's the first place that we look when something breaks. And none of that on its face is wrong. But the question I want to spend the rest of my talk on is whether that's really the whole story. So here's the question I want to put on the table. Like, what if the instinct is right, but for the wrong reasons? What if the deploy isn't actually causing the failures, but it's still the thing that you're staring at when things go wrong? Because if that's true, it changes where you put your engineering effort. It changes what tools you use, and it changes what you teach junior engineers when things go wrong. So I went and I looked. I looked at 400 million production pipeline runs to really try to understand if there's a relationship between deploys and pipeline failures. So that was one full year of data, and I'll walk you through what they show. So a little bit of context so that you can calibrate what I'm about to show you. The numbers that I'm going to show you come from Astronomer's managed Airflow platform for the 2025 year, paying customers only. So that's like no trials, no dev environments, no internal Astronomer workloads. These are real production pipelines that I'm going to be showing you. If you haven't worked with Airflow, the unit I'm going to keep referring to is a DAG. And a DAG is really just a workflow and a collection of tasks that are chained together. So like the picture on screen is probably the simplest example that we have, which is like you extract some data, transform it, and load it somewhere. It's written in Python, it's scheduled on a cadence, and again, think of it as very fancy cron. Every time a DAG runs, that's one pipeline run, and across this cohort, we logged 400 million of them. So the first thing that the data shows is that failures are actually really highly concentrated. The cohort-wide failure rate across those 400 million runs is 7%, but the averages, but the averages two completely different populations. So if you strip out all the DAGs that fail at least 50% of the time, so like 1 in 2 runs, then that average drops down to 2%. So the 7% is real, but it's mostly sitting at a small tail. And so specifically when you look at the chart, 3% of DAGs accounted for 67% of failures that year, and on the other end of that, 60% of the DAGs almost never fail. So really, the production pipelines, it turned out, are actually doing pretty fine, and the reliability problem is not evenly distributed. So it's a very small population of pipelines dragging down the average for everybody else. So where do the failures actually live? And it turns out it was 3 places. So first off, about half of all failures across the cohort are concentrated on a single buggy runtime version. So that was basically people that went and they upgraded to a specific version that happened to be buggy and stayed on it for reasons. So customers stranded behind upgrades, carrying a disproportionate share of the reliability burden because they never really got off the version where the bugs lived. The second-ish thing was long-running workloads, which fail at 3 to 5 times the rate of the fast ones. And honestly, that's really intuitive. The longer something runs, the more chances there are for something upstream to flake or for a connection to drop or for a downstream dependency to time out. The duration is a risk factor. And then the third, there was a few thousand DAG runs that had a 97% failure rate. So it's like not 7, but 97%. So these are like the chronically broken pipelines. Something in their environment is structurally wrong, and nobody bothers to fix it, and they keep running, and they keep failing. So here's the thing that's worth pausing on. None of these patterns actually trace back to a deploy. The runtime stranding isn't a deploy event, it's the absence of one. The long-running workload failure pattern is about duration and upstream fragility, not about what shipped. And the structurally broken DAGs aren't broken because of a recent code change. They're broken because absolutely nothing about the environment changed. None of the big failure patterns in the data are caused by code being shipped. So, but the absence of evidence isn't evidence of absence. So I wanted to test this deploy hypothesis directly. And here's the setup. So a deploy event in the data set is any time a code was pushed to production. So that could have been environment changes, or that could have been changes to your pipelines themselves. So for every single one of those events across the year, I compared the failure rate in the 24 hours before the deploy to the failure rate 24 hours after. So that same environment, same DAGs, just adjacent time windows. If the deploys are actually introducing failures, the after window should be worse than the window before. That's the prediction. Here's what came back. And honestly, I was really surprised. Before the deploy, 7.94%, and after the deploy, 7.93%, so absolutely flat. If the deploys were causing failures, that number should move, but it doesn't. So the deploy boundary is empirically not where reliability actually lives. And I want to be clear, this isn't a small sample. This was 400 million DAG runs. This is every deploy event for an entire year across the Astronomer's platform. So whatever is making pipelines fail is happening, but it's not concentrated around the moment the code ships. So why does it feel like deploys cause failures? The deploy is really an attention anchor, not a causal one. So if you ship something at like 2:32 p.m., you watch the dashboards more carefully for the next hour to make sure nothing's wrong. And then if there is failures, you're going to notice them, which otherwise you would have attributed to just noise. So basically the point being that the failures were happening before the deploy 2, you just weren't looking. The timeline on screen is the version we've all lived. 3 failures earlier in the day that nobody flagged because they felt sporadic. A deploy at 2:32 to upgrade your airflow, one more failure right after, and suddenly everybody is like, why did the deploy break? Oh my God, the upgrade broke everything. The deploy didn't actually break anything, at least according to the data. It's just that the deploy is when you started actually paying attention. So if the deploy didn't cause failures, then what did? To get that started, I'm actually going to talk about a conversation that I kept having with one of my engineers at Astronomer. So we were talking about a feature, and I've been trying to explain something to a senior platform engineer that I really respect. And he's an excellent engineer. He came through application development and really is probably one of the smartest people I know. And here's the customer scenario. There were two DAGs in the same Python environment. DAG 1 pulls from a vendor API who had an auth library pinned to a specific request version. There was DAG 2, which calls a data science model that required a specific request version for async support. So the ML team went and they deployed it, and like I said, things didn't work, and they realized very quickly that these could no longer share an environment. So his response really was what I would have, to be honest, expected from him, and it would be a response that anyone would really give coming from application development. Like, just have the customer pick a version, just have them adjust their DAG code, or like really, if you insist on keeping them in the same deployment, have them containerize their DAGs, or use KPOs, Kubernetes pod operator. If you don't know what that is, that's all right. It basically, Airflow has these building blocks that are pre-bundled to do specific things. So in this particular case, the vendor team was not going to update their package. The ML team wasn't going to downgrade. And the ML team certainly was not going to rewrite that entire complex pipeline using like native Airflow building blocks in complete custom code just so that they can containerize it. Both pipelines had to ship by the end of the day, and ultimately speaking, it just wasn't going to happen, especially because this story was like pre-AI and pre-Claude Code. And ultimately speaking, none of the textbook moves were really available, so they were looking to us for a solution. And honestly, this is probably a conversation I had with him over a year. Every time we would bring up these scenarios, he kept reaching for code-shaped solutions, and honestly, in that example, like I know there was a code-shaped solution. It's not really, the point is more that not everything is solvable with code, and not everything ultimately is in your control. So the conflict in that case didn't come from anything we wrote. It came from something that was upstream outside of the data engineer's control, from a vendor's pin dependency and an ML team's runtime requirement. So this guy's mental model assumed that this data engineer controlled the shape of the problem, but really in data engineering, it's the data or the constraints that control the shape of the code. So here's the inversion, side by side. Like I said, in app dev, code controls inputs and behavior, and that produces outputs. So the developer sits at the top of the diagram, and they control both sides of the equation. You'll write the code defines the inputs it accepts, and the outputs are a function of what you wrote. In data engineering, though, the arrow flips. Upstream data will shape the code structure and the dependencies, and then the code processes the outputs. The developer isn't going to control the input, or the data engineer, I should say, isn't going to control the input side. The schemas are going to come from somewhere else. The arrival times are going to come from somewhere else. The encodings, the types, the distributions, the volumes, all of that originates from something outside of the code base that you're maintaining. So your code is really downstream of inputs that you don't own, and that's the inversion, and it's the thing that software engineering playbooks don't really account for. So here's what that inversion looks like in practice. Your DAG could be syntactically correct. Your unit tests can all pass, all 250 of them. Your CI/CD builds can succeed, and everything can run really well in dev. Everything looks green, and then all of a sudden, your upstream provider will drop a column overnight, and your pipeline raises a key error on user type. So yeah, the failure does look like a code problem because the stack trace points to something at the code, but it's not the code that changed, it's the world around it. And this is why CI/CD and code review feels a lot less load-bearing in data engineering than they do in app dev. In app dev, those gates cover the primary failure surface because code is the primary failure surface. But in data engineering, the primary failure surface is upstream outside the code base. A passing test suite, sure, will tell me that my code is correct against the inputs I expected, but it says nothing about the inputs I'll actually get, which can change and really do change on a whim without warning. Okay, so now let me talk a bit more about the data that backs this up. I went looking for a cohort of DAGs that degraded over the year. So like the ones that started fine and ended up being broken. There were 309 of them. So in January, these DAGs were failing around 3% of the time, well within normal behavior. But by December, they were failing 98% of the time. So these were really functionally dead pipelines. Then I check their code change exposure across that same period. So again, that's like Airflow upgrades, package version changes, Python version changes, DAG structural changes, and business logic changes. Basically, the whole list of things you'd expect to break a pipeline if code were really the culprit. And what I found was this. The 309 DAGs that went from healthy to broken had absolutely no more code changes than DAGs that had been broken from day one. So code change-wise, the degraded cohort looked identical to pipelines that never worked in the first place. The thing that broke them was not visible, at least in their code history. Now, the obvious worry with a result like that is measurement noise. Maybe my proxy for code change was just too coarse, or maybe the signal was there and I just couldn't see it. So I ran a positive control. I looked at DAGs that went the other direction, so from broken to healthy. If the real fixes show up in the code change signal, then the recovery cohort should look very different from the degradation cohort. And it did. So the recovery cohort had a median of 4 real structural changes per DAG. The 309 degraded ones had 1. So meaning that DAGs that became healthy had 4 times the amount of code changes than the ones that went from the other direction. So same proxy, opposite direction, and the results you'd expect. So the signal works when code changes really are the cause. And the fact is that it's flat for the 109 isn't a measurement gap, it's a real absence. So here's what I want you to take away from those 2 charts. The absence of a code change signal is the signal in this case. So the chips on the right are the categories I ruled out. So again, runtime upgrades, package changes, business logic shifts, Python version changes. None of these things predicted the degradation. And once you've ruled out the code, you're really left with everything else, which is in a data pipeline means inputs. The most likely culprit is upstream data variance. So again, schema drifts, late arrivals, input shifts, and so on and so forth. I do want to be honest with you, though, that this part is inference. It's not a direct measurement. What the data shows directly is that code didn't change. The likely culprit being upstream is just the most obvious explanation, but the load-bearing finding here really is the absence of the code signal. So one more piece of data I want to give before I give the framework, because I want to be fair to CI/CD here. The 7% prod failure rate we've been talking about isn't the only number. Dev runs in this same cohort and fail at about 15%. So that's more than double the rate of prod. So that means that code review, CI/CD, and all the deploy boundary practices, they are doing real work. They're catching a meaningful share of errors before these hit production. So layer 1, code correctness, is real. The point isn't that any of this is useless. I really was just trying to get you into the room. The point is that 7% in prod is what survives dev. It's like the floor, and it's a lower bound on the failures that the code deploy boundary structurally can't catch, no matter how disciplined a data team is. So whatever we build next has to address what the deploy can't see. So what is actually catching in that 8-point gap? It's pretty much everything that lives at layer 1. So again, that's syntax errors, import errors, failing unit tests, DAG parse failures, type and lint violations. The logic bugs a reviewer would spot in a pull request. That's the stuff that will get filtered out before code ever lands in prod. And it is, again, doing real work. CI/CD isn't a placebo. But look at the other side. These are the things that slip through, and what shows up in prod as the 7% is everything that doesn't have a code signature. So again, schema drift from upstream, late arriving data, encoding changes that you can't see until your downstream chokes on a value, partial writes, for example, that leave a table half published, or really just being on a buggy runtime version that piles up and a runtime fragility that piles up over long-running tasks. None of these things are testable at the code deploy boundary because none of it really is about your code. So the 7% in prod isn't a measure of how disciplined the team is, it's the structural floor, which brings us to the framework. So here it is. Deploy practices cover layer 1 of a 5-layer reliability problem. Most of the failure surfaces in data engineering, though, live in layers 2 through 5. So I'll walk you through them. Layer 1, which we've been talking a lot about, code correctness. So that's unit tests, linting, type checks, code reviews. This is where the typical software engineering default tools work and where CI/CD lives. It's real and worth owning, it's just not the whole thing. Layer 2 is data correctness. So that's null checks, unique constraints, accepted values, schema validation. Your code can be correct, but your data can still be wrong. This is the layer where frameworks like Great Expectations, Soda, Elementary, and similar tools live. Layer 3, that is time correctness. Time's the silent failure mode that almost no software engineering style test will catch. That could be basically, ultimately speaking, a DAG that runs on a schedule but processes stale data is correct at layer 1, but broken in production. Layer 4, state transition safety. So that's write audit publish patterns, stage tables, publish gates. This needs to catch things where the pipeline ran, the data passed validation, but is the write safe to read. So that could be partial writes, duplicate inserts, uncommitted state, like all these live at this layer. And then layer 5 is recovery and degradation. So that could be dead letter paths, stale but labeled data, idempotent backfills. The question this layer needs to answer is, when layers 2 through 4 fail, what does your downstream consumer get? The downstream consumer ultimately expects trustable data, even when degraded, and that certainly beats silent wrong answers every single time. So again, here's the gap. Most of the software engineering tooling conversation in data engineering is about layer 1. Most of the failures, again, are in layers 2 through 5. And again, it's not because layer 1 doesn't matter, it absolutely does, but because the tooling for the other 4 layers are younger, harder to implement, and less culturally dominant. We borrowed the CI/CD playbook from AppDev, we wired it up for DAGs, and then we declared victory. And then we spent the next 10 years getting paid for problems that the playbook was never going to catch. So if layer 1 isn't the whole answer, what is? Here's 4 concrete moves that you can make to take back your teams on Monday. So the first one is contract test your inputs, not just your code. Your unit tests will assume stable inputs, but inputs are not stable, as we've learned. Define what you expect upstream, the schema, the cardinality, the freshness, the value ranges, and alert when any of those drift. 2, treat time as a first-class concern. SLA misses and late arriving data are failures, so instrument them like failures. Ran on a schedule and processed fresh data are 2 very different things, and most teams only measure the first one. 3, design for the input surprise. If your primary failure surface is outside your control, graceful degradation isn't something that's nice to have, it's a reliability strategy. So make sure to build your dead letter path, label stale data as stale, make backfills idempotent. And then 4, know you're always broken DAGs. And remember that 3% of your DAGs may be generating 60% of your failures. So find them, triage them as their own category, and don't let them inflate your reliability metric or eat your on-call rotation. So none of these are glamorous, but they're actually where the leverage is. And if you remember nothing else from this talk, please remember these 2 lines. Time and data state are first-class concerns. They're not edge cases. They are not day 2 problems. They are the primary failure surface. Excuse me. And design for the input you'll get, not just for the input that you expect. Your test can only describe the world you imagined, but production will hand you the world as it actually is. And to bring it all back to the title of the talk, software engineering best practices didn't fail in data engineering. They just got applied to layer 1 of a 5-layer problem and mistaken for the whole thing. So layer 1 does matter. Keep doing CI/CD, keep doing code reviews. But the next decade of reliability work in data engineering really has to live in layers 2 through 5. So let's build for the other 4. Thank you.
Thank you so much, Constance. She'll be taking questions if there are any. Please follow in line here and you can ask.
It was a great talk. I love your 5 layers of problems to look at. I'm doing these things every day. One thing that helped us out a lot was taking, I think, your second suggestion, recording the HTTP payloads we get through integration with Betamax. And that will unit test your expected inputs perfectly. You won't catch it when it changes, but you can go exactly to where the problem is and get a new recording and take care of it right away. The other one about time-based things, our friends Sentry downstairs have a cron checker, or it'll catch when your crons run or don't in time. And that has been a lifesaver for catching that kind of problem because it is really tricky. So the cron monitoring in Sentry is fantastic, and then record your inputs and test them just like you're saying.
Yeah, no, absolutely, and thank you very much for the advice. It's good to know about the Sentry. I didn't know that, so I will be checking that out. Okay, well, if there's no other questions, then thank you very much, and please do come speak to me whether you loved it or if you want to just get mad at me for bashing software engineering practices.